So there's this command that I'd like everyone to run ideally in your home directory. Let me just check that it works, but then I'll. Yeah. So just go ahead and, so you want to, in your home directory, maybe parallel with that data folder, type this command. And if it fails, put up your red sticky. And if it succeeds, put up your green sticky. So if you've already opened up your IPython notebook, you may want to shut it down or open a new terminal in order to run this command. Sorry, so just do the one at the bottom. Let me just do this. I only want you to do this one.
Can you put that in the Etherpad?
Yeah. So I'm going to put it in the Etherpad real quick. Sorry, guys. At the bottom.
This is different than a lot of the folders that we downloaded in the system.
Yeah, so that stuff's been changed since I asked you to download it. So this is going to be the most recent. You wherever you would like.
Testing out when to get installation. I just created the view. This is going to be super useful for getting started tomorrow morning.
So green stickies once you've succeeded.
That's not.
Oh yeah.
Yeah, so you got the installation works?
So people got the,
This is actually the
information
you need for.
probably works to be.
Actually, do like the code control, close the whole terminal, like accept the application totally. Okay, we can start. And just click into a new one. And now you can do.
So the thing that I,
Sometimes you don't restart it.
normally on Windows, in Bash, in Windows CMD, you just do activate, not source it, because that's actually activate that bash script. That of course doesn't work in Git Bash because it's a bash script.
That one?
But it doesn't seem to ship the activate, that's each script.
I'd come
Work in Bash.
It should be somewhere.
The question is whether they should just work from CMD. Should be fine as long as you're in some time.
Yeah.
Yeah, so an account on Windows definitely push in and activate that bash script, which is on path.
Oh, I see what you're saying.
It's a CMD script, right?
Do it. I think that's the right choice.
Yeah, I don't know. They
What is the
shipped the
URL?
activate, but as they say.
It is it's etherpad.org.
Isn't that last week? It's not the same.
It's not showing up.
I am currently there.
Oh, yeah, right.
Am I not? Maybe I'm in the wrong Etherpad.
Yeah, look, but you're the only person on this.
Hup, I'm in the Etherpad from last month. I do these a lot. Yep, that's the one from Berkeley. Sorry.
So
Okay. I was not there. You didn't know?
Sorry. I was in the wrong one. Done. Sorry, folks.
We go again?
Here? Yeah. Yeah, scroll all the way to the bottom,
that next one,
and then, yeah, copy.
that's what people activate, that, which an account that shows.
Did you hit, reload? Sometimes it's, oh, somebody clicked the way I launch it.
I just did. I finally made it to the right Etherpad. Oh, good call. Thank you. Go forth. Be brave. Do the things. Thank you.
Oh, okay. Here we're fine. Okay.
All right. Green stickies if you've done it. Red stickies if you are stuck. If your fingers aren't on the keyboard and you have no sticky up, I will be confused. It's fine.
Do I need to change the date my Python? I heard that it did.
Yeah, well, so this, it looks like you've got the newest version there, so it should be. Yeah, I think that should be. Yeah, I'm not sure why your screen is split.
Because I think it's
Very nice, everyone. So contained inside of what you've just downloaded is the course materials for this whole course, including the Python section here this afternoon. And so this afternoon's section is about using Python in the most basic way. So like, how many of you have used Python before? This is a SciPy conference, right? So it's pretty few. Many of you are here to learn it for the first time and get used to it so that you can understand the rest of this conference. So I hope that you'll be able to keep up and pay attention. We're going to start at the very basics. So if those of you who have like done it before, you know, try to help out your neighbor if they get stuck, and try to stay involved anyway, even if it gets a little boring. And in the future, so what we have here in this directory is a whole lot of lessons that Software Carpentry has created that will not get to all of them today. We're going to cover an introduction to Python, then we're going to load some data and interact with it, and then we're going to talk about loops and lists and analyzing data from lots of files at once. And we probably won't get much further than this, but we'll go over at least creating functions and probably errors and exceptions. But we'll just see how far we get in this afternoon, and the rest of it will be available to you to look at later if you're not super familiar with Python, and they're actually really easy to follow along just by yourself in these lessons. So those of you who have successfully executed this command, you will have a directory right where you just executed that command. You'll have a directory called 2015-07-06-SciPy. And in that directory, there's also a directory called Python. And so what I want you to do is use the shell command cd that you learned in the last, or maybe already knew from the last session, to change directories into the SciPy repository, which we'll get to what Git repositories are tomorrow, and then into the Python directory within that repository. So go ahead and change directories into that Python directory. If you type ls, you should see something sort of like this. It's pretty long, but at the top you'll see some of these ipynb files. Now, so what I want to show you is there's like a whole lot of ways to spin up a Python instance and start doing Python programming, right? The way that we're going to interact in this course with Python is with the IPython notebook, also known as, which is a part of the Jupyter notebook. But we won't go into the details of that. But it is a way to write Mathematica-like, MATLAB-like notebooks where you can document and run code in the same place. But there are other ways to instantiate Python. I'm going to just very briefly show you other ways to do it before we then jump into the lesson. So if you want to like run Python, you can just type Python into the terminal, and it'll plop you into what's called an interpreter. Okay, and the Python interpreter here is just these three little lines, right? And you can execute commands, and the simplest is print hello world. And we'll get to do this in a couple different instances, and you can see it has printed hello world. So all you have to do is type Python and you should see it. You should type exit to get out. I forgot to source activate again, so don't type what I'm about to type. I just noticed that I'm in Python 2.7. Don't type this current command. Okay. All right. Now, that was great. You can also type IPython, which is a fancier interpreter for Python. The cool feature of this is that it has, you can use the same print statement, but tab completion will give you more interesting stuff, and a question mark will give you help. And there's a whole lot of other cool things that IPython does, but this interpreter is like a little more sophisticated than the general Python interpreter. To get out of this, you also type the exit function. So to get out, just do that. So those are two ways to enter a interactive Python environment. Sometimes you can also write scripts and run those scripts, which you've already done. In order to run the setup test script, you type Python and then the name of a file. But today what we're going to do is the IPython notebook option. So those of you who are stuck in one of those two interpreters, please put up a little red sticky. Use the exit parentheses command to get out, and you may still be stuck. But someone will help you. So for now, if you are sitting in that directory that says Python, you want to type IPython notebook in that directory and hit enter. And your browser should open. So that's all I did. I typed IPython space notebook, this command right here. And then I hit enter, and my browser opened. If that did not happen, please put up a red sticky note. Yeah, it might take a second.
First time you open a notebook.
It can be a little slow. Excellent. So now, the first thing we're going to do is this 00 intro notebook. So scroll down and click on the one that says 00 Python intro. So what I did here was I clicked on this guy right here. Don't click on the one with solutions because it'll be not as exciting for you. So you click on that 00 Python-intro and you should see this. Put up a green sticky note once you see this. Great. So in programming, we have this notion of things. Some of them are variables, and some of them are objects. And we won't get deep into those objects until a little later. But the most basic kind of things in Python are these variables. And those can be of different types, including integers, which are just like 1, 2, 3, 4, floats, which are like 1.2, strings, which is like your name in some quotes, and some other special variables. Now, in the IPython notebook that you've just opened, in order to execute stuff, you want to type Shift-Enter. And you can execute any cell, including the text cells. So type Shift, click on one of these cells and click Shift-Enter. There's a lot of talking. Is everything okay? Okay. Okay. So it executes the cell. So for example, in this first one that has an in, so you can execute the text cells, but they don't actually do anything. In the first input cell that says a thing, you type the number 2, and all it does is spit out 2. It hasn't saved it to any particular variable name or anything, but you can say 2, and what the IPython notebook will do is spit that back out. Like this is the object that you're talking about. That's sort of like just print this object. And you can print numerous things in a single cell with the print command. Now, if you put 2, 3, the only thing I just want you to know that will print is the last one. So in the IPython notebook, so not Python itself, but in the IPython notebook, if you type 2, 3, 4, 5, 6, the only thing it will print out is the last one. So you guys can try that. But in order to print multiple things out, you can use the print function. Okay? And so print is a function that says, type this out to the output. And so print 2 means take the integer 2 and execute the print function on it. So print it, and then take the string variable hello and execute the print function on that. And so it should print 2, and then a line break, and hello, right? Okay. I can attempt to do so. I'm going to try Command plus. It was fine. It was fine. Is that okay? Bigger? Yes. People are happier. Thank you, everyone. There's some way to get rid of this top bit, Thomas. What is it?
On the view menu.
Yeah. Thank you. View, toggle. It was just so that you can see more. Okay. So then so those things aren't stored in memory. You can't use them later. We're just printing them out. In order to store them and use them later, you might give them a name. So you can say A is the number 2. You want to give A a value. You know, like you might say, my age is 17. Then you would say A equals 2 to set the value A equal to 2. You could set the variable B equal to the value hello. Now you can see the syntax highlighting here in the IPython notebook where the string is red, the integer, all numbers are these green colors. True seems to also be a special object, and in fact it is. It's what's called a Boolean. So Booleans are either true or false. There are many different ways to, so some people use 0 and 1 to indicate that. And in Python, the keywords reserved for true and false are true and false with a big T and a big F. And those, therefore, are syntax highlighted. And you can also use the print function to print all 3 of them at once. Okay, so what we're doing here is setting A equal to 2, B equal to hello, C equal to true, and then we're printing them all. So execute that cell, and you see that it all prints out on one line, rather than above where different print commands are executed on different lines. So keep that in mind also. Fun fact, so I just told you what the types of these items are, but Python knows this also. So you can say print the type of A. So the function type is just like the function print, except what it does is return the value, naming the type. And so print type A should print integer. It should print the same thing as if you typed print int, okay? Because int is what we're talking about. And so what it says is class int class bool. Yeah.
How do put spaces in between printed on one line, but how do we
That's just the way that the print function is executed. So it doesn't matter what type of object it is. It knows that because the commas are there, they're different variables. So those commas in between A, B, and C say print all 3 of these. And it's just the way that it's implemented to print it prettily. It's like the pretty print nature of print.
So if you wanted to concatenate,
Yeah, you'd have to turn them into a single object. And we'll get to that actually pretty soon.
I noticed you're doing shift enter and it asks us to do control enter up there.
I think it asks you to do shift enter. Oh, it looks like it does say control enter. Does that even work? Yeah, I guess it does. Oh, but it increments. Does it increment with shift enter? Yeah. But shift enter moves you to the next one, whereas control enter keeps you on the cell. So you can so if you type control enter, if you keep typing it, it just keeps executing the one you're on. If you type shift enter, it moves you to the next one. So you can shift enter all the way through a notebook. So that's what I usually find myself doing. Good question, great question. So what happens when a new variable points to a previous variable? Okay, so A equals 1, and then you say B equals A equals 2. Now what is B? Sorry, this is not in Python 3 syntax. So it will give you an error unless you put parentheses around it. So this is a good opportunity for me to just very quickly state the difference, one of the many differences between Python 2 and Python 3. So Python 2 has a whole lot of things that people wanted to change for a long time, but were they to change them would be backwards incompatible. So over time, the developers of Python slowly made a list of things that they would really like to change about the way that the original language was written. And they decided to wait until Python version 3 to become backwards incompatible. So this print function is actually a really visible instance of that. So if you don't have these parens around the B, it works in Python 2, but it doesn't work in Python 3. So in that notebook that you have, that one print statement is not in Python 3. It's not Python 3 compatible. So just execute that and you should see 1. Anyway, the point is, what happens is that if you say B equals A, you're setting the value of B to the value of A at that moment. And some of you who are used to pointers and references in a certain manner might find that a little strange, because what it's doing is pointing at the value of A as it currently equals. It's not pointing at the place in memory, because you then change A and B doesn't change. So this is making a copy of A. This syntax isn't pointing to whatever A is holding all the time. So if you update A after you set B equal to A, then B will not update when you update A, because it's pointing at 2 in this moment. It says, well, you're saying here is not B equals A, you're saying B equals, 1, the current value of A. Does that make sense? Clear as mud? Questions? Yeah.
You say that was new in Python 3 as well? Or?
No, just the print function here. So you guys have in your notebook this, and it will give you an error, and that's because we're in Python 3. And so you must treat print as a function and not as a keyword in Python 3. Commands that operate on things. So we've already seen 2 commands, print and type. And storing data and variables is great, but what you want to do is let the computer perform a lot of operations on things. And so one of the things we've already done is the equals operator. So A equals 2 we've already covered. It's actually like a type of function, B equals 3. And you can use these other operators like plus and multiply and exponent. So this is A to the power of B. This is very like Fortran-y for those of you who remember that. And divide. Okay. So let's go ahead and execute that. You can see that A equals 2, B equals 3, and you print A plus B is 5, A times B is 6, A to the B is 8, and A over B is 2/3. So that's great. Now something to keep in mind, actually, in terms of dividing integers, is another difference between Python 2 and Python 3, is that in Python 2, if you divide 2 integers and their result is something like 2/3, it'll round to the nearest integer because you're dividing 2 integer types, whereas Python 3 does it the way that you're expecting and gives you the decimal point. And so that's another backwards incompatible thing that changed in Python 3. So we've all moved into the future. And so we don't have to worry about that because we're all in a Python 3 world now. So you never have to have that oops. But many people in the Python world have had that oops. And so you'll see a lot of tests in Python code double checking whether that's happening or not. Okay, so that's great. So there are also operators for strings. So you can actually add 2 strings together. So this gets to your question earlier, like what happens if, what if you want to print things concatenated? And the beauty is that in Python, the plus sign works on 2 strings. And so hello plus world is hello world. And hello times 3 is hello, hello, hello. And that's actually incredibly powerful and not common in older languages. So check it out. Fun fact, you can't divide, because what does that mean? If you were to divide a string, it's like a little meaningless, and so the computer doesn't have like any better notion of what that would mean than you do. So unless you can think of a really like obvious thing that would mean, yeah. So that was great. That was a couple operators. I hope you're shifting through and testing some of these things out. And Boolean operators compare 2 things. So I said earlier that Booleans are true and false. So the Boolean type for a variable can only equal one of 2 things, either true or false. And so logical operations that you see like A equals B, like that question, does A equal B, should be either true or false. It can't be like kind of or sometimes or maybe, it's like true or false. And to get those out, we use these Boolean operators. This is common in lots of languages. Greater than looks like this. Equals means is. It's a check though. You're not trying to set 3 equal to 3. You're just checking whether or not 3 equals 3. And You can also use the or and and to combine Booleans. So in the case of print A, what it's printing is the Boolean 1 greater than 3. Is 1 greater than 3? No. So it prints false. And B, 3 does equal 3, so it prints true. The third value is either A or B true? Yeah? And the answer is true, because B is true. But are A and B both true? No. So that Boolean equals false. So you can extend these Booleans into combinations of Booleans. So you can have logical ands and logical ors, and they read or and and. So it becomes a much more readable, English readable language. In a lot of other languages, or is just like 2 lines, and is like a couple of ampersands, and it starts to get a little cluttered. But in Python, it's just A or B, true, right? So that's very, very lovely. And you can try out a couple of those. So like, why don't you take a moment and try out a few that you might be interested in. I can tell you that not is kind of a fun thing. Oops, that doesn't work. You need is. So that's kind of fun. So it is, in fact, the case that A is not B. And you can say that in Python, which is kind of sweet. You got to be careful with it, but it's pretty cool. All right, so that was really fun. Now, functions. So these are going to be pretty familiar with people who've used programming languages, and you've seen print and type. There are other functions that operate on most like reasonable variables. Len is length. So often you will want the length of a string or a list, and we'll get to what those are too. And so len is a function that works on many different types of variables, including this string. So what do you think the length of hello is? You can all count. It's 5, that's correct. All right, and round. So what do you think round probably does? It rounds the number to the nearest integer. That's correct. And so what we should see here is print type 3 should give you int, print len hello should give you 5, and print round 3.3 should give you 3. Yeah, success. Right, so fun fact, in IPython and the IPython notebook, you can type round question mark, and it'll pop up with this little window that's full of help. It'll say, oh, it gives you a given percentage, and you can see like, oh, it not only this, but it has an optional parameter that is the number of digits of precision you want in your rounding. Yeah, which is pretty cool. And so you wouldn't have known that had you just like not looked at the docs, but the docs are embedded here in the IPython notebook. And you guys can all thank a few people in this room for that. And to get out, you want to click on that little X. There's a little X at the top of your help. Another fun fact is that you can print parentheses and type tab. I think that can be very, in this case, it's not that helpful. But there's some fun things that you can do. Like you can type row and tab complete to round. And so fun facts, fun facts. So there you go. And if you want to see just what arguments it takes, you can type round question mark and then hit, oops, and then hit tab. But it doesn't look very nice, as I said. All right. So in this case, you can see the actions of round happening. Just as I've said, you can add this optional decimal place precision manager. So, you know, if you change that to 3, it should give you 3 decimal places of pi. If you hit 0, it should give you 3.0, right? That's the significant digits after the decimal that you want, right? And what happens if you give it 7, right? It only gives you as much as it knows, right? Because we didn't have 7 decimal places, so it just gives you what it knows. It doesn't throw an error, so keep that in mind. All right, fun facts. All right, now let's very quickly take a moment to express that all the things I've just shown you are part of the built-in Python library. So that's all stuff that already exists in Python, and you don't need anything fancy. But what we've imbued your computers with, or you probably did beforehand, is a package full of Python and a bunch of scientific Python packages and a bunch of other helpful stuff that comes in like Anaconda or Canopy and is like generally the topic of this conference. Okay, and they're full of useful stuff, okay? And so the way that you use those packages is by importing them into Python. You have to have them installed on your computer, and you want to import that functionality into your workspace so that you can then use the functions in that package. So I'm going to tell you that there is a numerical Python package called NumPy, which you've probably heard of. And in order to use it, the typical way to do it is to import NumPy. You're saying, bring this package into my workspace. And because NumPy is a lot to type and I'm a super lazy programmer, let's just call it NP every time I want to refer to NumPy. Things that are part of NumPy are going to be referred to as a part of the NP package. Okay, so you shift enter on that one. If you don't shift enter, the rest of this will look a little funny. So go ahead and be sure to shift enter. Now, to see what's in this package, you want to type np dot and then hit a tab. And you can scroll through all of the coolest things that are in this package. In fact, not just all the coolest, but all of the things. So let's take a moment. There's something called complex in NP because NumPy has a notion of complex numbers, for example, that it deals with, and conjugate, and it has arrays and floors and cool stuff like that, right? And so you can see lots of these cool things. So each of you scroll through this, so type np dot, or like enter the cell and hit tab, and then find a function that you think is interesting. I'm going to pick is Fortran. And then I'm going to hit question mark, shift enter, and I want to find out what that function does. So get help on a function in the NumPy package by doing that. So np dot tab, find something cool, hit enter, put question mark, and hit shift enter, just to see how that all works and feel the IPython notebook interface for yourself. So the key is this, at the dot, you want to type tab to get that menu. So that's pretty fun. Of the coolest things in NumPy, you're often going to use the really basic math functions. There's like the square root and pi, and in fact, Python has another math library called math, and you can use that, and it has a lot of these functions. NumPy is going to be the one that you want to use for arrays, and so a lot of math is just implemented in NumPy too. So, you can get the square root of 4, and you can get the number pi, and you can ask for the sign of pi. So beautifully enough, things are named exactly what you want them to be named. Cosine of pi is cosine, right? Stuff like that. So I'm pretty sure cotangent is also, yeah. So, you can play around with that. So briefly before we move on, let's just say what we've been doing with that dot syntax here. So I've accessed a function called square root that's part of NumPy using this dot, right? This is the same dot that I used before I hit tab. What it means is square root is a part of the NumPy object. NumPy itself is a package, but it's an object too. Everything in Python actually is an object, and more or less. And if you say NumPy, like np dot, then you have access to all the things in the NumPy namespace. So all of the objects in that namespace, including the functions and attributes of NumPy, one of which is square root. And so let's use a method related to other basic things. So these are, in the simplest, okay, let's just go through the explanation. So we're not going to teach object orientation, but in the simplest terms, you want to think of an object as a thing that contains data about it and functions that can operate on that data. And Python objects, for example, strings contain a set of characters and all the functions that you might use on a character, on a set of characters, things that are specific to strings. So instead of normal function arguments, you could do something that's only really going to make any sense on a string, like capitalize, right? So the string class has a function called capitalize because it's something you would want to do to strings. And so you create a string called hello world, A equals hello world. And you can print the type of string, right? But that's something you can do to any variable. Something that you can do to strings only, you can see with a dot. Capitalize, count, ends with, etc. Right? Is printable, lower, lots of cool stuff, right? And capitalize is one of them. And the response is it capitalizes just the first letter because it's capitalizing in the sense of a sentence, right? The similar one for uppercase is a dot upper, which I'm not sure is a function, it might be a method. Yeah, a dot upper, right? A dot replace L with X gives XXO Waxard, right? So you can actually use the replace function too. So try those out. Pretty cool. They're methods. So pretty neat. So these are methods that work only on strings. So as an exercise, so I know that's been a lot of talking, but it should have introduced you to all these concepts. So go ahead and go through this little exercise. The idea is that we want to go through, Thomas, did you want to go through this whole thing before we get to the NumPy one, or just keep going?
As much as.
Yeah. All right, let's do it. Okay, so let's go through this exercise, see how quickly everyone gets through it, and we'll accommodate from there. So throughout this lesson, we're going to be building towards a program that calculates the variance of some measurements that we have available. Okay, in this case, we have height in meters is available. So the first thing that we want to do is convert from this to, from inches to meters. So inches and meters, just keep note. The idea is create a variable, sorry, I keep clicking on it, called inches and meter. Create a variable inches for your height in inches, however you want. Divide inches by inches and meter and print the result so that you can convert your height in inches to your height in meters, okay? So in order to do this, there's an empty in at the bottom of this exercise. So start with step 1, create a variable for the conversion factor called inches and meters. Note that we have given it to you, okay? So go forth and do this. When you're done, put up your green sticky note and do it in this empty input slot. So green stickies when you've finished. Red stickies when you're stuck. These are your instructions. Step 1, create a variable. Hey, man. All right, Azalee's going to come here. So you should have, it looks like everyone's almost there. So you should have come up with something pretty similar to what I've got here. Inches in meter equals 39, because I've given you this expression here. You have to do a little calculation in your head. I am too lazy, so I'm 5'9½", so I typed 5 times 12 plus 9.5, okay? Because I don't like to multiply, and I like the computer to do everything. So my brain is better for other stuff. Yeah. And then I divide, and I print it. So that's the last part, and you should get the, you're nice and tall. Fun stuff. So that was pretty fun. Now you can set variables, write some calculations. It's pretty great to be able to calculate your height, but we can actually do a lot more with programming, or else you wouldn't be here. So in science, we often deal with a lot of things that are a little more complex than a single number. Usually it's like lots of numbers, lists of numbers, dictionaries of keys to values, and arrays full of numbers. And so NumPy actually is great for those arrays, and Python itself has concepts for lists and dictionaries, and something called tuples, which you may not have heard of outside of this context, and we'll go through those very quickly. The most flexible type of container in Python is the list. They're declared with square brackets, okay? So if you say A equals blueberry, strawberry, pineapple, you've created a list with how many elements? Could you guess? 3 elements. And they are strings, probably, yeah? And you can print the list, and then you can check that it is of type list. Yeah. Lists can be indexed. So if you just want to get blueberry out of the list, you want to use the index for blueberry. You want to say, I want to get the first one. And in Python, the first one is 0. It's indexed by 0. So some of you used to Fortran or MATLAB are probably not comfortable with that, but you will become comfortable. So if you print A0, then you get blueberry. If you print A1, then you get strawberry. Fun facts, you can get the last item in the list with negative indexing. So you can type -1, and it will give you pineapple. Because sometimes you want to search in reverse through a list. So, fun fact. And you can get the second to last item, which is strawberry. For really long lists, sometimes you are really interested in the last one rather than the first one. So this is super helpful. And indexing in reverse is often helpful for certain algorithms. So, you can access entire ranges by slicing. And the way that you do that is with a colon. So remember A equals blueberry, strawberry, pineapple. And to get the first 2, you would type A, 0, colon 2. Now, note that 2 is actually the index of the third one, and it's lopped off. So it's uninclusive. So those of you who are comfortable with bracket notation for a range, the first one is square, and the last one is a curly brace. So this is, okay, so mathematicians will note that this syntax 0, colon 2 in math world is really that, okay? So it's not including the number 2 index object, which is the third thing. So just keep that in mind when you're ranging stuff. You can also leave off the start or end if that's confusing and easy to forget. You can say I want everything until 2, or everything after 2 by just leaving off the index. It'll assume 0, it'll assume first, or it'll assume end, right? You can also list the whole thing if you wanted with an extra syntax with the colon and nothing else, and you can ask for everything up to the last one in this manner. So in this case, -1 is the same as 2 because there are 3 things in the list. So give that a shot. Make sure you understand it very quickly, and then we'll move on. So lists are objects like everything else, right? And so they also have methods. The kinds of things that you want to do to a list is add stuff to it, print stuff to it, pop stuff off it. Sometimes you want to add whole ranges of stuff. So sometimes you want to add two lists together, and you do this with append. So in this case, if you append banana to A and then print A, what you get is blueberry, strawberry, pineapple, banana. If you append the list 1, 2 to A, what you're doing is adding a single element that it itself is a list. So the fourth element in this version is itself a list, okay? And the way that you can tell is print A3, which is the fourth element, okay? It is the object print my obj. Okay, so oh, sorry, I can't count. 4. Right? No. Where did it go? 1, 2. Oh, there's just so many bananas because I kept appending. Here, I'm going to do it the easy way. -1. Okay, so that object is 1, 2. Okay, I've repeatedly done this thing, so I need to like restart this A definition to make it make sense. Let me just do that. Okay, so this is what it means. So you can have a list in a list, is what I'm saying. So you could recursively have lists of lists of lists of lists. Okay, this becomes somewhat powerful when you think of matrices as lists of lists, but you don't actually want to store matrices this way, but you may find a use for lists of lists of lists. Another thing that is clear from this is that different kinds of objects can be stored in a list. So the first 3 are strings and the last one is a list, but that's okay. You're allowed to store different things in a list. So pretty good. New Python users may actually note that these collections actually store pointers. So in the way that I said earlier, A equals B was this copy, that's not true for lists. So it's like actually, in the case of lists, it's different. So as we said before, A equals 1, B equals A equals 2, B ends up being this number 1. You guys remember that? Right, wasn't it? Yeah. But in lists, A equals 1, 2, 3, and then you say B equals A, you can change, it's actually a reference. So when you're saying A equals B or B equals A, and there are lists, then it's not a copy, it's by reference, right? You can see that when you print B, it has updated, right? So this is different than what it was with just integers. So simple things are going to be copies, and more complex things are very often not going to be copies, they're going to be references to the old one. So in order to do that, it's actually possible to use a copy method. So you can copy them instead. So C equals copy A. Oops, nope, A dot copy, right? Yeah, and then you can say print C, you can say A2 equals 10, and print C will still print C as it was before, right? So the way to get an immutable, or not immutable, a copy rather than a reference is to use this copy method instead, when you really mean copy instead of reference. Is that clear as mud to everyone? Yeah? Sorry about that. Who has a question about that references versus copies issue? Yeah?
What does that pop function mean?
Oh, it pulls one right off. Yeah, sorry, I sort of skipped right over that. But you can see in this case, if you take, if you A dot pop, then it takes one off of the end. So in this sense, in this one, there were 5 items in the list, and the last one was this list. And once you type A dot pop, it pulls it back off. So it pops it off the end, the back end.
If you set something equal to A dot pop, would it have gotten 1, 2?
Yes, that is correct. So what she's asked is a great question, and it is, if you say B equals A dot pop, what is B? Yeah.
Does A change?
A has changed to be missing the last item. That's correct. Yeah. Very good, very good. Fun stuff. Okay, so we have an exercise here. Store a bunch of heights in meters in a list. Should be very quick. Store a list of heights. Append your own height using the append method and get the first height from the list. Bonus, if you're interested, extract the last value in 2 ways. In the second case, presume you don't know how long the list is. Give me a
So,
scan, so.
do you want to go do dictionaries and NumPy arrays, and then we'll break and come back and start on the
Yeah,
other?
I think that makes sense. Yeah. Hopefully the break will be timed well with new coffee.
It's 2:15.
2 meters is pretty tall, right? It's like mat. 2 meters is mat tall.
How many giants do you know?
Lots of 300-foot giants.
Meter?
300-meter giants. So green stickies up when you're done, red stickies up if you get lost. If you're not interested in doing it, you can just put up a green sticky.
We're catching our breath.
As you should.
You're a bit fast,
Okay,
just to,
all right.
to admit to being
I'm really
slower than
actually,
you.
I'm glad you brought it up. That's what I do. That's actually why I do the exercise, so that I don't go way faster. I'm eagle hearing. Do eagles hear well?
So the IPython, that was installed when we installed Anaconda?
That is correct. IPython and the IPython/Jupyter universe are installed with Anaconda. As is NumPy and SciPy and all the cool stuff that people are going to talk about.
So
And many of the things that people are going to talk about that are not in Anaconda, that are part of this conference, will eventually grow to be mature enough to be part of that packaging world. All right, so, I scrolled up too far. So I just made up some heights. I had my height stored previously in a variable called meters, spelled some funny Britishy way or something, I don't know. Software Carpentry, fun aside, Software Carpentry is actually made entirely of volunteers. So all of the lessons and stuff are these like really international collaborations between people volunteering their time. And so you get a lot of like British spellings meet like American spellings, meet Canadian spellings, meet, yeah. Okay, so I append, using the append command to the height list, my value that I had stored previously. If you don't remember what it was probably called meters, but if I'm 1.2 meters high, then that's what you would say. I think I'm taller than that. I think I'm 1.8 meters high-ish. I can print the first value with height 0, as you know, and you can print the last value with height -1. There are two other ways to print the last value. One, I know the length of the list is 5, so I could just type 5, or I know the length of the list is 6, so I want to use the index 5, right? Or I can use the len function to find the length of the list and then subtract 1. Now, comparing the last one with the this third to last one, you can see maybe why we use this shorthand syntax for the end of the list, right? You're just saying len -1, len -2, len -3. So that -1 is just a shorthand for that. Fun stuff, fun stuff. So you should be able to print that out and see that you are lovely and tall. Great, so then we're going to go over a couple different other complex, slightly more interesting data structures other than lists, and one of them is tuples. So tuples are just like lists except for two things. One, you use parentheses rather than square brackets, right, to indicate that they're tuples. And it's immutable. So if you want to make a list that doesn't change over the course of your program, which sometimes you want for safety, then you want to create a tuple. So they appear a lot in situations where you don't have changing lists. You have some indexed list of things that you want to use forever. But otherwise, everything is pretty much exactly the same. They're often used instead when the position of a collection is super critical and you don't want it to change, or when you want to prevent any accidental modification of those items from elsewhere in the program, right? So pretty obvious. So if you want to say xy equals 2345, that's how you do it. Looks like coordinates, so it should be comfortable. And xy0 is the first one. The only difference here is that this indexing doesn't really work with a tuple because you can't set something. You can't say this index equals something else because you can't change it. So you see you get this exception out. So you can try, but it'll throw this this exception type error. Tuple object cannot be assigned to things, right? So the indices are great for accessing the variable, but you can't then assign the variable to anything once you've accessed it if it's a tuple. So that should be clear. What we've just seen, actually, as an aside, I want to share with you is a traceback error. So you see that it's spit out this error. And the way that you probably want to read these traceback errors is from the bottom up. The bottom thing is going to tell you what went wrong. And further up is going to go more into detail from where it came from, because they put the most recent call on the stack last. So in a computer program, you have functions that call other functions that call other functions. And the most recent one to throw the error is at the bottom, and the one that caused it at the very beginning is at the top. And so you can see here that you see it's a type error from the bottom. It says tuple object does not support item assignment. Understood. Now where did that happen? It gives you a little code snippet so that you know where it is in the file. And in this cell, which has 3 lines, it is that third line. And you can tell because it's got an arrow pointing to it to help you find it, right? And so that's how you read an error. So next time you get something like this that's really scary, don't just freak out. Just read it, and it'll tell you what's wrong and where it went wrong, and the explanation will typically tell you why. And if it's super cryptic, Google it. That's programming. Okay, probably all of you knew that, but it's pretty much everything you need to know to, huh?
Sometimes we put quotes around it, because you're like, it's this exact phrase, tell me what it means.
And if you're the only person who's ever Googled it, just go get a coffee. You're gonna need it. But probably you aren't, and there's a whole suite of Stack Overflow answers to help you. Okay, dictionaries. So we've covered tuples, we've covered lists. Dictionaries are a slightly more exciting thing, and they're actually in the depths of how Python works. Actually, dictionaries are used in the language really often. In actually how the language is instantiated, how it's implemented. Anyway, so dictionaries are this collection when we want to store things next to names. So you and I just wrote a list of heights, but if you were collecting the heights of your neighbors, you might want to label this is Elizabeth's height, etc. And so, that's a nice thing to have. And the way that you would do this is with keys. Now, if you have a whole list, for example, of different conversions, you might want to name what you're looking for as the key, and then the number. So here, inches and feet, inches and meter are the keys, and their values, their definitions, right? This is a dictionary. So you look up a word, and you get the definition. In a dictionary, you look up a key, and you get the value, right? So in this case, the key inches and feet has the value 12. The key inches and meter has the value 39. And the way that you make a dictionary happen is with curly braces. You separate key value pairs, you separate keys from values with colons, and you separate pairs of keys and values with a comma, right? So you see curly brace, key, colon, value, comma, key, colon, value, comma, key, colon, value, comma, key, following curly brace, okay? And then you can print it, and it'll just print out nicely. And you can then access the inches and feet in feet variable, or the value associated with inches and feet, which is 12, using its name rather than its index. Okay. You can add a new key value pair using this indexing syntax, just like you did with a list. So you would, except in this case, what it's doing is setting the key equal to this number. So if you wanted to add meters and miles, then you would say converters, square brackets. So you're still using that square brackets indexing syntax, but inside you don't put the index number, you put the key name. And if you want to create a brand new key, you just invent that key name and equal sign and the value, and you can print it. Now, you may get from this example that keys can only be strings, but that's not the case. Keys can be any immutable type in Python. And what did we just learn was an immutable type? Tuples! We just learned that tuples are an immutable type. So you could actually make the key to your dictionaries tuples. So, so for example, you might say, I'm just going to insert cell below. So you might say positions equals, and I'm not sure why you would do this, but you might say 1, 2 equals, maybe you're playing Battleship. Katie ship, right? And 3 to Elizabeth ship. 1, 3 missile, right? And that's a valid dictionary, and you could say positions. 1, 2. So you can say, what's at the 1, 2 position? And it would say Katie ship. Right? So you could play Battleship with dictionaries if you're really interested. So fun facts all around. So there's just one more data structure. Yeah.
How do you start? I just saw you do.
Oh yeah, I just type and type, huh? Ah, very good question. So there are a number of ways. So I did it the way that is super lazy. I just typed insert cell below, but there's a whole bunch of wonderful shortcuts in the IPython notebook, which you can usually get to with a question mark, but I'm not sure why I'm not getting there. Yes. So you can say plus. Nope. Control plus, command plus? No. Yeah, I don't know either. Now, what's the keyboard shortcut to get all the keyboard shortcuts? It's usually question mark, right? Is it H? Yes, it is. Thank you, dears. So you can see all of the keyboard shortcuts in IPython notebooks with H. But don't be in a cell, just like be outside of a cell when you type it. Because then it'll just write H in the cell.
So if your cursor's in a cell, press escape, and the border of the cell will change from green to grey. And then say, you can't type in that cell anymore, but then you can use keyboard shortcuts.
So you can click on the out or something. So the final data structure that we're going to go over before we take a much needed break here after lunch is NumPy arrays, which you're going to work with for the afternoon. For the afternoon, this later part of the afternoon, we're going to get a little more powerful and do some science with Thomas using NumPy arrays. And so I'm going to just show you what NumPy arrays are before you dive face first into using them. And these NumPy arrays are super powerful, and you're going to see them a lot in scientific code. NumPy arrays are a huge workhorse, and we call them ND arrays because they're n-dimensional arrays, okay, and that's how you instantiate them. They are not part of the core Python libraries, as we talked about. They're part of the NumPy package, but they're super useful. So Software Carpentry thinks of them as like a core piece of Python. The reasons that they're useful, so you can easily perform element-wise operations on them. So sometimes you want to do something to every element in an array of values, and they're good for that. The arrays can be n-dimensional, so that means that you don't just necessarily have a matrix or a 3D mesh of values. You could have a 4D, 10D, 12D matrix. So you can index in multiple dimensions. So there's no limit. Well, there's probably a memory limit to how many dimensions you want to put in an ND array, but I don't think there's an actual cutoff. And there's no equivalent to append. So it's a good thing to keep in mind. However, you can concatenate ND arrays.
There's a NumPy append. It depends on array to an array. Like you can't.
Right. Yeah. So they can be concatenated, I think is, but there's no like dot append. You have to like do this. Yeah. So as we did before, you want to import NumPy as NP if you hadn't already. And we're going to start with the simplest situation where we have a list of numbers and we want to make an array out of it. And in fact, what we want is to have two arrays that are each 1 by 3 here. All right. And what we say is we have some list from somewhere in our world, and you can just say A equals NP, so NumPy, dot array, and so in this case it's calling the array function out of NP, NumPy, and using it, which is a constructor, so it's going to construct an object for you from a list. A list, in your case, is 234. It's the list 234, and it's what NumPy array does is create an array object that contains the values 2, 3, 4. It's of size 3, right? It's got like 3 values. And it prints as 2, 3, 4. It doesn't have any commas because it's not a list, it's an array. And so actually its order is very important and stuff like that. And it's of type numpy.nd array, right? So you typed array, and what you got is nd array. You can also type nd array, but it's up to you. So what do you then do with that? Well, now that you have A equals this 3-element array, you can raise it to an exponent. You can even take the sign of every single element in that array with just one function, right? You can multiply that array by another array. So these are 2 vectors, for those of you who are more physics-y. And so A star B should give you this vector multiply, but A dot B should be distinguished from that. So, keep in mind that these are actually different operations. So one's a scalar function, one's a vector function.
A times B, like if you have 2-dimensional element of B in the second element. It's not matrix multiplication.
Right, it's vector multiplication. And the A dot is going to be your scalar function, and the A times is going to be vector vector, right?
I think that works for vector when you start getting into.
Oh, it's element wise. So it's 1, 1, 2, 2, 3. Yeah.
More than one dimensional.
Yeah, so you can see from this example that it's doing element wise in this case, right? It's multiplied 2 times 5, 3 times 6, and 4 times 7, which is not necessarily what you want to do when you want to do this kind of vector multiply, right? The cross product is not what you're getting, but you still get a vector. So exactly as Azalee said, so it's not doing the vector multiply like you're used to. It's doing this element-wise thing. Boolean operators work on arrays. So you can say, is A greater than 2? And is B equal to 6? What do you think that means? So is A greater than 2? If A is a 3-element matrix, 2, 3, 4, is A greater than 2? What do you think you're going to get at?
I guess the length, I don't know.
Yeah, so interesting fact. You get one value for each value. So you get false for the first one because 2 is not greater than 2. And you get true and true for 3 is greater than 2 and 4 is greater than 2. So it's a mask. So for those of you interested in the name of that, it's a mask. It's a Boolean mask. And so you get the same things out of print B equals 6. So only one of the elements of B is actually 6. It's the middle one. And so you get false, true, false. If C equals A greater than 2, so if C equals that mask, false, true, true, then you can print the type of C, and you can print CD type. So the data type in the array has its own type. So if it's an array of integers, the data type of the ND array is int. If it's an array of just floats, then the data type of the array is floats. And in the case of the situation where you've set C equal to the Boolean mask, the data type of the ND array is bool. So that's what you're seeing here. So ND arrays have a value called dtype. You can see that like print b.dtype will give you what? What do you think? Int, correct. Int 64, in fact. So 64-bit int. All right. Indexing arrays is very similar to indexing lists. So in this case, indexing arrays that are just 1D looks exactly like a list, in fact. But you can have two-dimensional arrays, in fact, multi-dimensional arrays. So it gets a little more complicated once you start indexing more than one dimension. So let's see what it looks like. First, you have to create a more than one-dimensional array. One way to do that is the NP random function. So NumPy has a random number generator, and in that you can create an array of random numbers if all you give it is the size. So in this line, we're creating an array, a 3x3 matrix of random numbers. And so what we then do is we're going to print C, that random array of numbers, and then we're going to print a string that has a carriage return, an end line character. That's just so that it's cleaner looking when we print it out. You don't have to have this. Don't worry too much about that. And then what we're going to do is print a subset of the indices. And so you can see from the first, from like the x-axis, we're printing 1 to 3, and from the y-axis, we're printing 0 to 2. So let's see what that looks like. So first of all, the first thing we did was print the 1D array, A 0 to 2, and indeed we got 2 to 3 because remember A was 2, 3, 4. C, NumPy random, does indeed give you a 3x3 matrix of random numbers. Now see how this array has two sets of square brackets, and that's to indicate to you that these are contained in one another. It's to help you identify the rows versus the columns. And so here you have rows and columns. It just is a prettier way to print it, right? And then if we want C 1 to 3, what we're really asking for is the second row through the third row, and 0 to 2, this just these first 2 bits. So we're asking for this lower left-hand corner in this case, and indeed that's what we get, right? So if you want just this lower left-hand corner, you want to drop the top row by not including the 0th row, and you want to drop the rightmost column by not including the 3 here. If you wanted the whole thing, it would be 0, 3, 0, 3, but to get part of it, you would just use this. All right, now the next thing that we do is, give me just the 0th row, but give me all the columns, and set that equal to A. So set this 0th row equal to A, gives you exactly what you expect, 2, 3, 4, and then the rest of the matrix. So in this line, we are assigning a value to the top row. What do you think should happen if you try to set this to like a single number? What would you expect to happen? How could you check it out? That's correct. So it actually does a lot of things that like you intuitively would want, but if that's not your intuition, then like be careful.
If you initialize a matrix and you have it all integer values, but they're going to become floats, does that work out okay, or does it truncate to ints? Or?
Yeah, so let's just do that to see how it happens. In this case, for example, what you're trying to say is you want b equals, let's just use our initial one from before actually. So we have, the A object, if you say A 0 to 3 equals 0.1, then that object, so you remember print A was this initially, well, let me set A equals, sorry, it's all screwed up because I've now done it too many times. Let me just do this. Boop. So I'm re-executing that. And then what I'm going to do here is I'm going to say print A down at the bottom here, and A0 to 3, let me just do it up here so I don't screw everything up. So it's clearer what I'm doing. So I've created A just in the same way that I did before, and then I print A, and what I'm going to then do is reset A0 to 3, and A.dtype is what I want to print, right? That's to answer your question there?
Yeah.
Yeah. Boop, boop. And indeed, it stays ints. All of them. Right. So if you think your array may someday be floats, and the reason for this is largely like memory allocation, as you might imagine. So when NumPy sets up that array, this is also related to why you can't append as clearly. You want to concatenate very like specifically rather than just like dynamically append things to an array object. It has to do with memory allocation.
So does that mean that if you reassign to floats, that it's going to dump all the decimals?
Yeah, so indeed that's what's just happened here. So here we've got A list equals 2, 3, 4. We set it equal to a NumPy array. So the NumPy array is initially all ints. And then I print A just to make sure that that's truly the case. And then I reset A, all of them to equal 0.1. You could even say 2.1 just to make sure that you understand, it's clear. And print A at the bottom list is just 2s, and they're all integers. So you lose all those. So if you ever want it to be a float, you want to start out as floats.
So you can assign the data type when you initially do it and has extra parameters?
Yes. And indeed, let's just show how that works because it's kind of, it's a nice syntax. If what you want to do is make that happen, dtype equals float. And now it's 2.1. Yeah. So that's great. So that's more or less NumPy arrays. There's one exercise that I think would be good to, there were two more things I wanted to show. 3 more things. You can index arrays with other Boolean arrays. So this is kind of an interesting experience here where, this is not quite right because I've now screwed up what A is. to show that, but okay. So this should work for you. So arrays can be indexed with other Boolean arrays. So I've just shown you there's this mask, false, true, true. And if you want to print A where A is greater than 2, you just want to print those entries that are greater than 2. You can say print A, index, A greater than 2. So you can do this in lists too. It's called list comprehension. And in NumPy arrays, you can only do it with these Boolean mask key things, but it's pretty cool. So in this case, you want to print B only where B is where you want to print B only where A is greater than 2, right? You get the same mask, false, true, true, and you apply it to B. And so you say print it, not the first one, but yes to the second one and the third one. Is that clear? What's happening there? Yeah. So you can print B only where A is greater than 2. It's kind of cool. You can see if you have two related arrays, that's one way to sort of combine this information pretty quickly in a very simple syntax. They have attributes in addition to methods. So we talked about how methods are something you might say like C dot. We did this with capitalize, but they also have attributes, just data associated with them. So shape is the tuple, rows times columns, and then times other dimensions. And so 3, 3 is your size. And prod is like if you just take the product there. So you can ask exactly what it means, c.prod, question mark, to get the official definition. It is the product of the array elements over the given axis. If you don't give any axis, and in fact there's only one axis in this one, it'll just guess for you and do a default. So it's good. 2 more things and then we'll have an exercise. So there are ways to make a lot of handy ways. So we went through one way to make arrays with random numbers. There's also a way to make an array full of zeros with the np.zeros method, and you just give it a shape. np.ones does the obvious thing. It gives you ones. And then np identity. If you are doing some linear algebra, it's the identity matrix. So it's all zeros except for the diagonal. Okay. And in however many dimensions you want, which is pretty sweet. Just saying. And you can also make arrays of sequences of numbers. So if you want it to slowly increase over an axis, NPA range 0, 10, 2 will give you 0, 2, 4, 6, 8. Okay. So the reason it's skipping by 2 is because of this 2, and it's giving you in the range 0 to 10. So it's almost time for a break, but we should probably just take a little moment. If you want to, you can do this exercise, or you can go take a break and come back and look at this exercise. And once we're done, it'll be Thomas's turn to wow you.
So after an array, if you wanted to know everything that you can do to an array, how do you drop down?
Yeah. So in our case, A is a type of array. You want to type a.tab. So a.tab will give you this list of lots of cool stuff. You can take the conjugate, you can make a copy, you can fill it with some other value, take the mean. Really good stuff, really good. All right, so you're free to do that exercise anytime during the break. Be free. And put up your red sticky if you need help. But you're free to break now.
Okay, so I think everybody's back from the break. So before we go on to the next lesson, just the solution to the exercise there. So we have the list of heights that you would have done in a previous exercise, and so the first bit asked you just to turn that into an array. So we do that just with np.array brackets heights, and then assign that array to a new name. So I'm calling it heights array. You could have called it something else. Calculate the mean. So we call heights array.mean. And it asks you to create a mask of all the heights greater than a certain value that you can choose, and find the mean of the masked heights. So I have the masking bit is this. So heights array greater than 1.65, we'll create a mask, so it's an array that has true everywhere that the number is greater than 1.65 and false everywhere that it isn't. So in this case, I haven't actually called the masked array and the mask array anything. I'm just using it directly. So I'm saying heights array where this mask is true, and then take the mean of that, and then to the first bonus bit asked to get the number of heights greater than your threshold. So again, I've made the masked array, selected the elements from this array where that mask is true, and then used the len function, which is a standard thing in Python, to find how many elements are in that new array. And I haven't dealt with the second bonus bit, but well done if you got to that. So we're going to leave that notebook there. There's some more stuff in there, but we're going to get to that in another format. So if you go back to the listing of notebooks that you had here and click on 01 NumPy. Okay, so this is kind of the original starting point of this set of materials. We felt that it was kind of a weird starting point, so the bit that we just went through is kind of like a getting up to speed bit. So some of this material will now go a bit quicker. So we're loading NumPy again. So we're just bringing in this piece of code that someone else has already written so that we can use the functions from it. And then this time we're going to use another function called load_txt, which will load a file from disk into a NumPy array. So the file, this string here gives the path to the file that we want to load. So it's in a folder called data, and there's a file called inflammation01.csv, and then there's an extra argument here saying that that's comma delimited, so it's a CSV comma separated value format file. So if we run that, then we'll get an array which contains the data that was in that file. So this is some background stuff on variables that we've already gone through, just assigning to variables and doing basic maths with them. So resuming with NumPy. So we've done numpy.loadtxt again, but this time we've instead of just letting it display that array, we've stored that into a variable. So an array, just like an individual number or anything, you can store it in a variable to refer to it. So our variable data here is this array, and it's a NumPy ND array, which is what we expected. As you just saw before the break, NumPy arrays have a dot shape property. So we created relatively small arrays because typing in lots of numbers gets boring quickly. But here, with this data that we've loaded from the file, the shape is 60 by 40.
And so I'm not sure if we covered 2D indexing, but if you have more than one dimension and you want to index into it, then you just put the indexes with commas between them. So 0, 0 means the first row and the first column, remembering again that we always count from 0 in Python. So 3020 will be the 31st row and the 21st column, which is the central value in our data. And you can also do the same thing with slicing. So here we're saying we want the first 4 rows and the first 10 columns. So the result, I'm just going to actually make this a little bit smaller again so that it displays a bit more neatly. So the result is 4 rows by 10 columns. So we're just kind of cutting up the array of all the data that we've got. And you can do the same thing without starting from an edge. So we can say we want rows between, so starting at row number 5 and up to but not including row number 10. So we're taking kind of a slice of 5 rows, and then again in this case the first 10 columns is what the 0 to 10 means. So this can be useful if you're looking at a big chunk of data and trying to work out like what's going on in there. You can look at just a small slice of it, and you know that can be a more reasonable thing that you can understand. And again, as you saw, you can, if you do maths with a NumPy array and just an individual number, it reuses that number and does the operation on every element in the array separately. So if you say data times 2, it multiplies every value in that array by 2 and gives you a new array. And then so double data was based on the whole of our big array, and if we slice data and we slice double data, because double data came from data, the same slice gives you the same, like the matching bit of those two arrays. So the numbers in the second one here in that little chunk are the same as double the numbers in the chunk from the original array. And again, you can also combine arrays and arithmetic operations. So here it will do the operation like adding between each number in the first array and the number in like the matching place in the second array. And there are rules for like what it will do if one array has more dimensions than another and things. It can do clever things with that. But yeah, I think the important case for now is just when the arrays are exactly the same shape, it will do this matching up of the elements. And again, you can use the mean method on the array to find the average. And by default, if you have a 2D array of numbers, this actually takes the mean of over all the numbers, so it just collapses it down to a single number. You can also give it arguments, so it will take, the mean of every row separately or the mean of every column separately. And some more useful methods. So this data is supposed to represent some inflammation over the course of some illness for 40 patients over 60 days or vice versa. So the array has a a max method and a min method, and STD is for standard deviation. So again, like mean, we've got a 2D array, and if you call them without arguments, they're just taking the maximum or the minimum or whatever statistic over all the numbers, so you just get a single number in the answer. But you can also tell them to work on the rows or work on the columns. So here we're going to cut up the data again. So here our rows represent individual patients and the columns represent different days. So we're following each patient over, I forget how many days. So this expression means we're taking the first patient, and then the colon is the slicing syntax, but we're not giving it a maximum or a minimum. So we're saying we want from the beginning of the array to the end of the array in that dimension. So that means the first patient for all the days in the data, and then we're going to, with that array, take the maximum. So maximum for patient number 0, because this is counting from 0 again, is 18. And we could keep doing the same thing for each individual patient like this, but that's not very efficient. So we could instead say we want to take the mean across axis 0, which in this case means the I need to stop and think about this. I always get confused with axis numbers. So this means that we're taking the rows, taking the mean down the columns. So we're across the rows. So we're getting the mean across all the patients for day 0, and then the mean across all the patients for day 1 and for day 2, and so on. And if we did this with axis 1 instead, then we'd get the mean across all the days for patient 1 and across all the days for patient 2, and so on. So here are our means across our means for each day, and we can check the shape of this. So this is now a one-dimensional array, so it's just one sequence of numbers, and there are 40 numbers in it, so that matches up the number of days that we were expecting. And similarly, if we do axis 1, this should now be the average inflammation for each patient, and if we were to do the shape of that, then we see that is, we know we have 60 patients, so this kind of basic sanity checking just helps you to make sure that you're doing what you think you're doing. So then getting into something a bit more visual, like you have these lists of numbers, but it's not very easy to really see what's going on with a set of numbers like this. So we can instead start plotting things. So the first thing, so there's a couple of things going on here. So this matplotlib inline, any command that starts with a % is like an IPython special command. This is just telling it that when we plot graphs, we want them to appear inside the notebook rather than somewhere else in a separate window. So just like when you're plotting inside a notebook, you just always start with this little command. Now we're loading another library called matplotlib.pyplot. So this is, matplotlib is a library for drawing graphs and plots of various different kinds, and pyplot is kind of like a high-level interface that makes it easy to do simple things with that. So then from that pyplot module, we're calling imShow, so which means show image, and we're giving it our data. So our data is a 2D array, so it can represent that as this kind of heat map. So on the x-axis is our 40 days and presumably 40 nights, and on the y-axis is our 60 patients. And the colours represent like the numbers that are in that array, so in this case the inflammation values. And you can see that for each patient it's kind of like, it's starting off low and then going high with these like yellow and red colours before going back down to the low numbers on the other side. So this immediately gives us a much clearer idea of what's happening with those numbers. So here we've taken the average across axis 0. So this was the average for each day across all the patients, and now we're plotting that. So we're using another function from matplotlib pyplot, which is this plot function, and there are various different ways that you can call this, but kind of the simplest one is you just give it a sequence of numbers. So we're giving it this array, and it's just going to plot those, assuming that the x-axis is just like counting up counting up from 0 to 40 in this case, and using those numbers as the y positions on the graph. So you can see that there's this very kind of neat triangular shape which looks a bit suspicious. Like, if you study biology, then like it's never this neat, is it? Like if you see a graph like this, then you should be thinking that something suspicious is going on. Physicists probably have neat graphs like that, but I wouldn't know. And so we can do the same thing with taking the maximum of the data. So before we did this in kind of 2 steps. So we took the mean and stored it in this variable average inflammation, and then we plotted that. But if you don't need to refer to that variable again, then there's no particular need to store it. You can just create that, summarize the data in that way, and do that. So doing it inside the plot function call kind of calculates that data and then immediately gives it to plot. So when we do it with the maximum, this is now looking even more suspicious. It's a perfectly triangular graph. It's rising in an absolutely straight line and then falling in an absolutely straight line, and the center is dead on day 20, which is the length of our sample. And if we take the minimum, then it's again looking suspicious. So it's not quite a perfect neat triangle, but it is going in these kind of series of steps up and then down. And we should just note at this point that matplotlib is kind of like automatically adjusting the scale to the numbers that are in the graph. So here, the biggest number in the graph was 20. So the scale on the y-axis went from 0 to 20. And here, the biggest number in the graph is 5. So it's only giving us a scale up to 5. But I think if we plot them both on the same graph, then you can kind of see how the numbers relate to each other more clearly. So just that's something that catches me out sometimes, is this automatically adjusting scale. If you plot numbers that you want to compare on different graphs, it can make it hard to compare them because the graphs can have completely different scales. So some kind of like putting all the stuff from that together and using some slightly more advanced matplotlib things. So we're loading that data file again, inflammation01.csv. This time, instead of just plotting immediately, we're creating a matplotlib figure, which is, so like a figure is the thing that's going to hold whatever graphs you're drawing, and we're saying we want the figure size to be 10 by 3, and because Americans, that's 10 inches by 3 inches. And then we're putting three subplots onto that. So we're going to have three graphs side by side. And the way this works is we've got 3 numbers in those calls. So the first number is the number of rows you want, the second number is the number of columns, and then the third number is like which subplot you're dealing with inside that. So when we say 1, 3, 1, you're saying I want a set of 3 graphs, 1 row, 3 columns, and then 1 is give me the first subplot from that. So the first 2 numbers have to match all the times that you call this, and the third one you count up. So that gives you these axes objects, which are like the boxes that you actually plot into. And then we're putting so set y label gives it a little bit of text that goes by the y-axis to describe what that is, and then plot puts your data onto that axis. So here we're putting the mean, the maximum, and the minimum side by side on this figure.
How will we maintain the same scale for the scale?
So in this case, I don't think there's a way to automatically do it. So you have to work out like what the numbers that you want are on the scale, and then you would say axes1 dot set y lim, and you give it the minimum and the maximum number that you want. So if I just copy that. So I know that I want it to be from 0 to 20, so I've just told each axis individually to go to that scale rather than letting it do its automatic scaling. And now they're all comparable.
So you should be able to use share y when you create new axis, then you can tell it that it should share the y-axis with the one that you already created, so that they all have the same.
So would you do that in add subplot,
so
or
if you look at the documentation for add subplot, then I think it takes a share. Otherwise. Yeah, it's probably buried somewhere in there.
should we just save it?
I will say Matplotlib has a lot of different options, and there's often multiple ways to do things. There are also a lot of examples out there that I'm sure we'll go to, and you can kind of look at the website, look at how different people have done it. But especially in Matplotlib, more than other libraries I use, there's just multiple ways to do things, and you can use the share or you can use the set limits. And there's, I would say I find the examples to be very easy.
It's share y without underscore, and you pass it as an argument axis1. Instead of true, you put axis1.
Yeah.
Oh, I see.
Which axis you want to share with?
Yes.
I see. So that should work. There we go. Thank you. So yeah, that's the better way of doing it.
Yeah. So the main advantage with that is, of course, that if you have an interactive figure, then when you zoom in one of them, then you can make all of it move at the same time.
Cool. So yeah, Jens is one of the core Matplotlib developers, so he knows this stuff better than I do. And yeah, as someone was mentioning there, there is a thing called the Matplotlib gallery, which is a part of the Matplotlib website. So it has lots and lots of examples of different kinds of graphs that you can make with Matplotlib. And if you see something that kind of roughly looks like what you want to do, then you can click on that, and underneath it there's the code that generated that. So I can copy and paste this block of code. If I can use a keyboard. So that's a very nice, quick way to get started with Matplotlib plots, is to find an example that looks like the kind of thing you want to do, and then copy and paste it, and just modify the code to use your data or to look like how you want it to look. Okay, any more questions from that before we?
Could you show me the one step that you did where you added another plot to the same plot that back there you had 2D plots and you wanted them both in the same frame or figure? Or
yes, so I just did the plot calls one under the other.
Right
Where did
there.
that? Somewhere. Yeah, there. So I just put the plot calls together in the same cell. Again, there might be better ways of achieving that.
Okay.
Yeah, I mean, that's a reasonable way to do it. There's a more object-oriented way where you can, like we've seen before, you create an axis and then you plot on the same axis, but for quick and dirty plotting, this is certainly.
Yeah, so there's like two ways to use Matplotlib. Like, PyPlot is the kind of like the quick and dirty interface, and like what we're doing down at the bottom here is more the object-oriented interface, which is a bit more verbose. Like you're going to be typing more stuff to get plots in that, but it's easier to see what's going on and to like add things to it. Sometimes with PyPlot, if you want to change your graph in what seems like it should be a simple way, you have to completely change how you're building it. Whereas this is kind of like a bit lower level and a bit more flexible.
The thing with PyPlot, right, is that it depends on the order of which you're doing things, because when you do several plots in a row, then depending on whether you did something in between, then it might go in the same figure, it will go in some other figure. Here you can actually plot something in some window, then go ahead and do something else on a different figure, and then come back to the first one. That's very difficult to do with PyPlot as it was, because it's just plotting in the one that's currently active, which may not always be the one you want to use.
So you have a different object for several different.
Yeah, so
you
the other thing is what's called a stateful interface, basically, that it has a state, built-in state, that this is the current figure that I'm working on. And then when you create a new figure, then that will be the current one. And then you have to switch back and forth, which is not obvious. Whereas this one, you explicitly said, on this figure or on this axis, do something, which is more flexible.
All right. So that was notebook number 01. We started at 00, just like Python counting. If you now want to open number 2, and I will just again turn off the header and the toolbar. So here again is the graph that we plotted at the end of the at the end of the previous notebook, just highlighting the fact that there's definitely something suspicious going on with this data set. But this is just one of a dozen data sets, and there are going to be more coming as more data is recorded. So we want to find a quick way to draw graphs like this for each data set that we have. So obviously, like, doing the same thing repeatedly is something that computers should be really good at. So this lesson is kind of about how to do the same thing repeatedly with Python. And you already saw that in Bash with the for file name in do and then done. This is going to cover the same thing in Python, but yeah, it looks a little bit different. So, like, here's just another kind of motivation. Like, if you want to print each character from a word on its own line, you could say print the first character, print the second character, print the third character, and so on for the number of characters that there are in the word. But that's, like, it's pretty boring to type, and it's not very flexible because, you know, if you do this, here we have a 4-letter word, but if you do this with a 3-letter word, then it prints out 3 letters and then says error. There isn't a 4th letter. Like, why are you asking for the 4th letter from this 3-letter word? And if you did the same thing with a 5-letter word, then you've missed a letter because it's only going up to 4. So this is the kind of thing where you want a loop. And so we have our word variable, and we can say for char in word, print char. So the loop just says, do this same thing for everything that you get from this object. So when you do it with a string, it gives you every character. If you do the same thing with a list, it gives you each object in the list individually. And as with Bash, it doesn't matter what you call this. Python isn't looking at that, so you can call it rabbit if you want, and that will still work exactly the same. But it's good practice not to call your variables rabbit unless actual rabbits are involved, because that makes it hard for you to understand what the program is doing when you come and read it later. So good practice for programming is to call variables things that makes it easy to understand what the program is, both because you have to come and read it later, and somebody else may well have to look at your code at some point. So giving variables silly names is not generally appreciated. So again, like, one of the advantages of doing this approach is that it's automatically flexible, so it will do however many characters are in the word. So it doesn't have a problem if the word is shorter than we were expecting, and it doesn't have a problem if the word is longer than we were expecting. If, you know, however long this string is, it will keep going. And you can even do this with there are ways to do things that are infinite, and we'll just, like, keep producing numbers forever. And you can have a loop over that, and it will never finish. But in some situations, that's what you want. So yeah, kind of just to re-emphasize the general form of the loop is you say for variable name in collection, and then inside the loop you can use that variable name to be, like, what you're doing for each thing inside the loop. So for instance, if you wanted to count some things, so here we want to count the vowels, then you can create a variable before the loop that's 0, so this is going to be our counter, and then inside the loop, so here we have the variable vowel, but we're not using it inside the loop. Here we're just, like, for every vowel we're going to add 1 to this counter, and after the loop has finished, that length has been incremented to 5. So that's just confirming that that statement inside the loop gets run as many times as there are things in this collection. And somebody was asking in Bash like why you have to put do and done. So in Python, kind of the equivalent is that when you start a loop, you put a colon at the end of the line, and then the bits that you want to go inside the loop are indented, and we normally use 4 spaces to indent that block, and then the end of the loop comes just when something is less indented than that. So you can have more than one statement inside this loop, and that will work. But as soon as you have some code that's not indented by 4 spaces, then the loop is finished, and it won't run that code until after it's gone through the loop however many times. So, and also just to note that the variable that the loop is using is a regular variable, which is you can use in your program after the loop. So here before the loop we've said set letter to Z, and then we use the variable letter for the loop. So it becomes A, and it becomes B, and it becomes C, and then after the loop, if we go and try to use it, it's still C. It hasn't gone back to Z when the loop finished. So the value that it was before has been lost. So just like be careful with the naming of your variables. You don't want to get rid of things accidentally. Yeah.
On that previous loop, is it possible to exit the loop before it finishes? If you're doing some condition within that loop and get out of the loop when it meets that condition?
Yes, absolutely. So there is a lesson on conditions in a bit, but just briefly, you could say, for example, if val is E, and then the keyword to get out of a loop is break. So that means just like break out of the loop. So here we've gone A, E, and then it's stopped there. So we haven't counted I, O, or U. And there is also, it's less clear if I put it here, but if I put it at the start of the loop, it will be more obvious. You can also say continue, which means like instead of doing the rest of this go round of the loop, like go back to the start of the loop and carry on at the next step. So if I do this here, it will effectively skip over E, because at this point it's got to this and said, okay, it's E, continue, so then it goes back here and carries on with I. So then just to remind you from the previous lesson, like if you actually wanted to count the number of letters in a string, you wouldn't have to go and do this kind of like making a counter yourself and adding 1 to it for every letter in the string. You can just use the standard Python len function, which will get you the length of a string or the length of a list. Okay. So this is asking you to use a loop to take a string and reverse it effectively, produce a string with the same characters in the other order. So if you want to have a go at that, and if you need help, put up a red post-it. So I'm actually going to show a couple of different variants of the solution for this. So the first one is the one I was helping someone with. So if we say name equals Newton to start with, so then you can again get the number of characters in a name by using len. So here there are 6 characters, and there's a Python function called range, which has this form. You can give it a starting number, a stopping number, and a step. So normally it counts up from your starting number to your finishing number, but if you give it a step of -1, you can get it to count backwards. So if I say range n0 -1, that will, I have to do this to see what it's actually going to give me. So that's counting backwards from 6 down to 0, not including the ends. So in this case, I want to use these as indices, and Python starts counting from 1. So I'm going to count from 1 less than the length down to -1, which it won't include. So now I have 5, 4, 3, 2, 1, 0. And if I do, so like in the vowels example up here, we started by making kind of like an empty variable at the start of the loop, and then we built it up inside the loop. So there we were doing that with a number and just adding 1 to it in each step of the loop. Here I'm going to do it, so just two quotation marks side by side makes an empty string. So I can say for ix, so that's kind of a convention. Ix is an index. So for index in this range, counting down, new name equals new name plus name ix, and then say new name. So here I'm again just creating an empty variable before the loop and then building it up 1 character at a time inside the loop. So that's one way. So as I said, I'm going to give you a couple of solutions here. There's a slightly neater way is that we can do something very similar. But instead of creating this range and iterating backwards through the loop, we can just do the addition the other way around. So instead of adding things onto the end of the string, we're adding things onto the beginning of the string, which will give us the same result, but it's just saves us a bit of typing and a bit of thinking when we look at the code. And then finally, the last way is the kind of Python cheaty way. So this is slicing syntax again that we used for our lists and arrays. And again, if you just put a colon with no numbers either side of it, it goes from the beginning to the end. And like we had with range, there is actually a kind of optional third argument for slicing, which is the step. So you can do : -1, and that will go through it backwards. So that one you weren't expected to know about, because this is supposed to be a lesson about loops. But that's like, if you actually wanted to reverse a string in some Python code, this is the quick and easy way to do it. All right, so that's the loops lesson. How are we doing on time? It is 4:10. Does this lesson go until 6? Am I right? 5. Okay, so we should press on rapidly. So lesson number 3 is about lists, which we've already actually gone over in the introductory part. but we'll just kind of like bomb through as a reminder. So we're constructing a list, so you use these square brackets and then a series of things with commas to make a list, and we're calling that this list of odd numbers odds. It's not very original, but it makes it clear what we're doing. And we're getting the first element from the list with square brackets 0, and the last element from the list with square brackets -1. So you can count up from 0 to go from the first element, and you can count backwards with -1, -2, -3, and so on to go from the back end of the list, the right-hand end when you display it. And we can loop over it again. So this is our same syntax as we were using with strings in the last lesson. We have our list, our container that we're iterating over, and this is the variable that we can use inside the list and indeed after the list. And so you can change one of the values inside a list, unlike with strings. So strings, like tuples, as we saw in the earlier lesson, are immutable. So once you've made a string, you can't change that string. You can make a new string and like assign that variable to the new string, but you can't actually like modify that string. So if you try to say like change the first character of this string to a lowercase b, it says, no, you're not allowed to do that. String doesn't support item assignment. So mutable and immutable data is kind of like an important idea to get your head around. So lists and dictionaries and NumPy arrays are all mutable. You can change part of them. Strings and tuples and individual numbers are immutable. So unlike in some other languages, in Python you can't say change the value of this thing by 1, or like, you know, change the value of this number by 1. You can say add 1 to this number and then store the result in the same variable, but that's not, you're not changing the value of the original number, you're making a new number. And that's kind of what the examples before, where you set b equals a, and then like if a is mutable, then changes to a affect b. But if you create a new thing and assign it to a, that doesn't affect b. So another way of mutating lists is adding numbers. So append adds to the end. There's also .insert method that will kind of stick a value into a list in any position you want. You can also del an item from a list will remove that item, and you can also reverse a list, and this is called an in-place reversal because it's affecting that original list. So Python also has a reversed function. So this again is being a bit too clever for me in this case, so that's returning a special iterator object, so I could use that in a for loop to go over these numbers backwards, but I can't just see the numbers. So we reversed our list once. Now if we say reversed of this list, then it gives me a new list with those numbers reversed. But if I look at those numbers, they haven't been affected by calling reversed on them. So this list.reverse changes the list itself. This reversed list gives you a new list in the opposite order, but doesn't affect the list you give it.
So what gives you a new list?
So this reversed gives you a new list, but doesn't affect, it's not affecting our variable odds, it's just creating a new list. Whereas odds.reverse is changing that list. And there's also, in a similar way, there's also a sorted function that gives me that list but doesn't change it, and a list.sort which changes the list. So we went through that one quite quickly, but that's because we already saw lists in the bit Katie was talking about. Yeah.
Do we use the reverse for the characters string instead of numerical?
Yes, so you can do reversed with a string, but I think it will give you, if I remember rightly anyway, it will give you one of these iterator objects. So yeah, it gives you a reversed object rather than, so you can use that in a for loop. And I think, can you do this? No, that's not going to work. That's just going to say. So you could actually, we could say that will work. So string.join takes the string that you're doing it with. So if I put a dot there, so this string becomes the separator. So if I put a dot there, it puts a dot in between each character, and then the argument to that is something that it can iterate through and get characters or short strings or whatever, and it will join them together into one long string. So yes, yet another way that you could solve the reversal puzzle. But yeah, I would probably use this one. I know it's arguable. This one is a bit clearer. But unlike lists, strings don't have a reversed method because you can't. That changes the list in place, and you can't change a string. Okay, so moving on to notebook number 4. So we're going to, going back to our kind of like analysing this patient data with inflammation and this sort of suspicious looking shape of the graph where it goes up and down very neatly. We now want to do that for a set of files that we've got with this data. And so we're going to use a library with one of these bizarre Unixy names that's a short word that doesn't really mean anything, which is glob. So we import glob, and then the main function in glob is also called glob. So we can say glob.glob, and this is, you saw this wildcard behavior in the shell where you can use an asterisk to mean anything can go here. We can do the same in Python using this glob function. So if we say glob star.html, that's going to give us a list of all the files in this folder that end in HTML. And as you can see, it doesn't give us them in any particular order, at least on my computer. It might differ according to your computer. So we would have to sort this list if we wanted to have them in a particular order. So, going back to returning to our example data, so our data is in a subfolder called data, and all of the data files we're using have a .csv extension, so we can get a list of all of them using glob and this pattern, and then we're going to sort them just so that we have them in a consistent, predictable order. And again, we're we're using this like little special IPython command to say that we want graphs to appear inside the notebook, and we're loading NumPy and matplotlib so that we can read these data files and we can draw plots from them. So we've got our list of file names. We're going to, for the moment, say we just want the first 3 files, just so it's easy to look at the results. And then we're doing a loop over these file names, so for f in file names, and then the rest of the code is the same thing that we had at the end of the first notebook after the break. But now instead of hard coding the name here, instead of just writing the name into the code, we're saying the name is f, so it's the name from the loop. So we're going to load each of these files and plot some data from them. And there's an error. We got name matplotlib is not defined. Okay. I see. So that should be like that. And I think that should do it. So if you also got an error saying name matplotlib is not defined, then on this line where it says fig equals, you just need to change matplotlib.pyplot to this plt.
Wait. So fig equals plt.figure.
Yes, so it should, in the notebook at present, there's a little mistake. It says fig equals matplotlib.pyplot.figure.
It's actually the import statement is the mistake. We removed aliasing and it's still.
Ah, okay. But then there's another PLT down here, so yeah, there's a mistake one way or another, and this is the quickest way to correct it. So now, underneath that cell, you should have these graphs. So it prints out the file name for each one that it's working with, and then it reads the data, calculates the mean, maximum, and minimum for each day across all the patients, and draws these graphs. So that was Inflammation 01 was our original, the data we were looking at first. Inflammation 02, you can see it has a very similar pattern. The maximum goes up and down in this this perfect triangle, and the minimum is kind of doing this stepping up and down. And then Inflammation 03, you can see it still looks kind of weird. There's something a bit different going on here. Is in this one, the average and the maximum look a bit more realistic, but in this one the minimum is 0 across all the days. So there's on each day there was at least one patient with no inflammation at all. So that's a different kind of something weird happening in the data. So this was a very short lesson. Are there any more questions about that before we move on?
Could you explain what does file names do exactly?
So file names here is just a list of the file names that we've got. So if I make a new cell here and type file names, it's just a list like all the other lists that we saw, except that these are just normal strings, but they refer to a file that's on the computer. So in f is the variable for the loop that becomes each of these file names in turn, and then when I do this load txt, I pass in pass in f, and that tells it to load that file.
Is that file names the Python command, or that's a Linux shell command?
So file names is just a variable that we made here. So there's nothing special about that word. I could have called it anything.
Important thing is glob. Is that?
Yeah. So glob is where that list of file names is coming from.
Which one of the modules does glob come from? Is it one of the things we imported in earlier? Yeah. Okay, I see it.
Yeah. So it's at the top of the notebook, and the module is just called glob. And yeah, when you're using this kind of pattern where an asterisk means anything can go in this bit, you might hear people referring to that as globbing. Okay, so if you want to open notebook number 5 now, this is where we get into like making the code do different things according to like what the value of some variable is, or check something in your code and do different bits of the code according to that. So here's kind of like the simplest possible example is where we're making a variable num that we're giving the value 37, and then we can test num greater than 100. So if we just split off a cell to do this, num greater than 100. So this is going to give us one of these Boolean results. So it will say true or false, and then you can use that in an if statement. So you say if condition, and this is something that will evaluate to true or false. And then, like with loops, the line ends with a colon, and then there's a block of code that's indented with 4 spaces. And the end of the indentation will tell us where this block ends. And so everything inside this if block will only be run if that condition is true. And then immediately after an if block, you can put else colon and have another block of code, and that's exactly what it sounds like. If there's the two blocks of code. If the condition is true, then it runs the if block. If the condition is false, then it runs the else block. And then anything that comes after that, like after it's done whichever of these bits it's going to, it will carry on with that code. So here, 37 is obviously not greater than 100, so it's skipped over this block, it's not printed greater, and it's done the second block instead. So it's printed not greater. If I changed this number and made it 137, then now when I do that, it will run this bit of code, and it won't run this bit of code. So this is kind of explaining illustrating the structure of what's going on there. Like in a flowchart form, it will take one of these 2 branches, and then after the if statement, they come back together, and it carries on doing the same thing regardless of which of those things happened. And the else bit is optional, so you can leave out the else, and in that case it just does nothing if the condition is not true. You can also have these elif, which means else if, So if there's more than two possible conditions, alternatives that you want to examine, then you can do if and then elif and then elif and then else, and you can have as many of these elifs as you want. So it starts at the if. If that's true, then it runs this. It runs the first block, the if block, and then skips over all the rest of the things. And if that's not true, then it checks each of these elif conditions in turn, and the first one that it finds is true, it will run that block and then skip to the end. So if more than one elif is true, then it will only run the first one.
Is there a rule of thumb as to when you use single quotes versus double quotes?
Not really. So with the strings, well spotted. In this case, we're using single quoted strings, and in this case, we're using double quoted strings, and it makes absolutely no difference. You have to use the same kind of quote at both ends of a string so that they match up. Like the only real reason is that if you want to like use a single quote as an apostrophe inside a string, then it's easier to do it inside a double quoted string. You can like if you put a backslash before it, then you can put it inside a single quoted string, but it's generally just neater. And if for some reason you wanted to do double quotes inside a string, then it's easier inside a single quoted string. So it allows both, but there's no difference between them, and there's no particular rule for when you should use one or the other, as far as I know. Yeah, well spotted. So then, similarly, you can combine conditions. So you can say, with this AND keyword, you can check that two things are both true. So this says if 1 is greater than 0 and -1 is greater than 0, then do this. Otherwise, like if either of them is not true, go to the else. So obviously -1 isn't greater than 0. And likewise, you can do OR, which checks like are any of these things true, and you can use parentheses and combine like multiple ands and ors to build up the logic. But like in general, more than like 1 or 2 ands and ors in one expression kind of gets quite complicated to follow. So we're going to bring our data back in and use some of these conditions to check for the two different like suspicious patterns that we saw in our data when we were looking at it by eye. So like the first condition that we saw was when there's the perfect triangle that goes straight up to 20 and straight back down to 0. So we're going to check for that by saying if like the minimum is the minimum of the data. What's that? Oh, so we're doing a so taking the minimum for each day over all the patients. If the minimum is 0 and the maximum is 20, then we can say suspicious maxima. If all the minima add up to 0, then that probably means we've got the dead flat line across 0 for the minima, so we can print another message. So here we're going to test that out again with our first file, inflammation01. So that does indeed say suspicious looking maxima. I see. So yeah, it's actually checking if we take the averages for each day across all the patients and then look at the first day, is that 0? And look at the 20th day right in the middle of the sample, is that 20? So if both of those things are true, that's a pretty good estimate that we've got one of these kind of like perfect triangles. Obviously it's not perfect. You might well want to go and look at that data more closely to check, but it's kind of a good first check to tell you which data might be dodgy. And then inflammation03 was the one where we had this dead flat line across 0 for the minimum on each day. And it is saying minimum add up to 0. So we've kind of sanity checked that the code we're writing is working for the cases that we've already seen. So it's always a good idea when you're writing code to just like keep checking that it's doing what you expect, because it's easier to find problems in small bits of code than to build 1,000 lines of code and then try to find all the problems in it. So I said before that when you make an if statement, the bit that you're testing has to come out to true or false. That's not actually strictly true, because Python will convert anything that's in an if statement to true or false. And so if we run this, we can see like which things got printed out. So the first one, like we said, if empty string, and that didn't get printed out. So an empty string becomes false. And then we said if word, and that word is true, did get printed out. So a string with some letters in works out as true for an if statement. And kind of like the general rule here is that like if it's 0 or it's empty, then it's false. And if it's non-zero, or it's a container that's got things in, or it's like basically anything else, it works out as true. So this is like kind of a handy shortcut. Like if you want to check, are there any items left in this list that I'm working through, you can say if my list, and that will be false when the list is empty. Okay, so there's an exercise here. So it involves a bit of mathematics. So work out some conditions that will be true if variable A is within 10% of variable B, and false if it isn't. And then check with the person next to you and see how does your implementation compare to their implementation, and try to find pairs of numbers where your solution and their solution will give a different answer. And again, if you put up your green post-it notes when you're done. All right, I think we're going to move along because we're short on time, and there's a couple more things we want to just kind of introduce before we wrap up for the day. So how would you do this? If A is 10 and B is 11, then we want to print true if A is within 10% of B and false if it isn't. So I'm actually going to use a little trick here called chained comparisons. So I can get 90% of B like that. And then in one expression, I can do if A is greater than that and A is less than 110% of B, like that. Now there's kind of a condition that wasn't really specified in the question, which is, it says like A is within 10% of B. Like what should it do if A is exactly like 10% above or below B? And the question, like the specification doesn't really provide an answer for that. So like, depending on what you wanted there, you could either do this with less than or equal to. So let's say for our purposes, we want to include the case where A is exactly 10% more or less than B. So here that's saying true, but if I put B up to 12, that should say false, and it does. Were there any quick questions about that exercise? Great. So another little trick, which is not really related to the rest of the stuff in this lesson, but is that, so instead of there's a lot of times when we want to change or do something with a variable and store the result back in that variable, like when we said x, count equals count plus 1 when we were counting vowels, or like one of the ways that we built our string Newton backwards was we said like new name equals new name plus this character. So there's kind of a shortcut for doing a lot of these operations is that where you would put x equals x plus, you can shorten that to x plus equals. And similarly, if you're doing x equals x times 3, you can do x times equals asterisk equals 3. So here, if I just delete that line. So here, x starts out as 1. We add 1 to it and store the result back in x, so it becomes 2. We multiply that by 3 and store the result back in x, so it becomes 6. So we'll skip over the exercise there for the moment. And another little trick is if you have two variables, so we're calling them left and right here, and you want to swap them over, like you could do this by introducing this other temporary variable and saying, I'll store my left variable in temporary for a moment, then I'll copy right to left, and then I'll take the temporary and put it back in right. Or there's this shortcut that you can just say left comma right equals right comma left, and that just flips them over in one go. So very briefly, before we finish for the day, there's this sort of really important idea in programming of defining functions. So you've used quite a few functions already, things like len and NumPy array and glob. So functions are something that take an input and return an output, and they can do other things. They can write files or read files or whatever, or they can print things out. And it's kind of like a really important notion, because these functions form the building blocks that you use for programming, and you start off with functions doing very simple things, and then you can put some of those together into a function that combines them and does some more complicated thing. And by kind of like building up these pieces in this way, you can make that's how much more complicated programs get made. It can't all be a series of instructions, do this, now check if this is the case, because there's just so many possibilities that the code would be impossible to follow like that. So these functions kind of like pull together a particular bit of the logic and say, this is how this is done, and then elsewhere in your code you can just say, this is an example of this function is how to convert from degrees Fahrenheit to degrees Kelvin. So you can define that once, and then anywhere in your code that you need to do that conversion, you can just say Farad to Kelvin and get the result. So the way you define a function in Python is this def for define keyword, then you give it the name of a function, then in parentheses are the arguments or parameters, which are the inputs to your function. So inside your function, these names will be variables that your function can use. And then, like with loops and if statements, we have a colon and then an indented block of code. So in this block of code, we're using this variable temperature, which is getting passed into the function. And often, but not always, a function ends with a return statement, which says this is the output, the value that's going to come back out of the function. So if I define a function like this, then this is how I use it. So I'm using the name of that function that I gave it, Farad to Kelvin, and I'm passing in a number which is this degrees Fahrenheit, and the output of that function, the return value, is coming back as the number in degrees Kelvin. And just that idea of composing different functions. So we've defined Fahrenheit to Kelvin. Here's a function that does Kelvin to Celsius, which is a very, very easy conversion. And then if we wanted to do Fahrenheit to Celsius, we could use the two functions that we've already defined. So we can say, I want to go from Fahrenheit to Celsius. I can convert so here's the input to this function. I can give that to my Fahrenheit to Kelvin function that I've already defined and get back a temperature in Kelvin. And then I can give that to my Kelvin to Celsius function, and the result from that is my temperature in Celsius. So I will leave it at that point. Matt, are you going to do some finalization?
Yes, just very...
So we might go into more detail on defining functions tomorrow if there is time.
Okay, any questions at this point for Thomas about Python, about anything else? All right, yeah?
You put that Fahrenheit to Kelvin in the time k there, in the argument instead of write the time -k.
Sorry,
Combine the second line and the third line, so time k equals Fahrenheit to Kelvin, right? Time. Put that one into the time in that Celsius argument.
So I think I know what you mean. So you can, yes, you could take this and put it directly in there.
Does that work?
Yeah, that will work. And then yes, you can also, so we don't have to actually declare this either. We can say return that directly. So now we've just turned our 3-line function into a 1-line function, and it's still doing the same thing.